The cross product has properties. I'm not going to read them all to you, but I will should point out a couple of things here. A cross B is equal to the negative of B cross A. The cross product is not commutative. Order matters. And the reason for that is what happens when we compute a determinant generally. If we interchange two rows of a determinant, then the result will end up having the opposite sign of the original. Remember that the rows, the second and third rows of a cross product represent the vectors A and B. And so reversing the order A and B has the effect of exchanging two rows. And then we can see that there's an associative property with scalar multiplication, and there's a distributive property, A cross B plus C, the cross product distributes over the sum. And then the interesting things with the mixes of the dot product and the cross product, as well as the cross product with applied twice to three different vectors. You can verify these by forming cross products using, say, A1, A2, A3, and B1, B2, B3, and just cranking through. Now let's look at a couple of geometric interpretations of the cross product. Given two vectors, A and B, so I'll make A the one that's kind of lower and B the one that's kind of higher. The cross product A cross B is going to yield a vector that is, as we said, orthogonal to both A and B. So here we have a vector A cross B, and it meets A at a right angle and it meets B at a right angle. Now there are actually two vectors that will meet both A and B at a right angle, and the other one is just as long as A cross B. It points in the opposite direction, and it would be actually B cross A, right? The negative of A cross B. How do we know which of these vectors points up and which of these vectors points down? There's something called the right-hand rule. To see what's meant by the right-hand rule, use your right hand, point your fingers in the direction of the vector A, curl your fingers in the direction of B, and the way your thumb is pointing will be in the direction of A cross B. Alternatively, if we were to start with the vector B, take the fingers of your right hand, point them in the direction of B, curl your fingers in the direction of A, and the way your thumb is pointing would be the direction of the vector B cross A. For another geometric interpretation, consider the vectors A and B and the parallelogram formed by A and B. The area of the resulting parallelogram will be the magnitude of A cross B. While we're considering the magnitude of A cross B, let me include a little note here. The magnitude of A cross B through an involved algebraic process that is in textbooks, the magnitude of A times the magnitude of B times the sine of the angle theta between A and B. You may recall that the dot product, A dot B, is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. Don't confuse the two. The cosine goes along with the dot product. The sine goes along with the cross product. And remember that because the cross product yields a vector, for this representation to make sense, we have to have the magnitude of A cross B. It follows from this relationship of the magnitude of A cross B that if theta is either equal to 0 or pi, that is to say, if A and B are parallel, then A cross B is going to be 0, well, the 0 vector. One more geometrical interpretation. Given three vectors A, B, and C, we can form a parallelepiped, which is basically a rectangular solid that somebody kind of smushed. And its volume is given by something called the scalar triple product. The scalar triple product is A dot B cross C. And note that this has to be computed in a particular order. B cross C has to be done first because its result is a vector. In order to form a dot product, I need to dot two vectors together. If I tried to dot A and B first, I'd end up with a scalar, and I cannot then cross that with C. It turns out that A dot B cross C is actually, it can be done by computing its own determinant, A1, A2, A3, B1, B2, B3, and C1, C2, C3. So that's the computation. How this is related to the parallelepiped is that it's the magnitude of A dot B cross C that gives the volume of a parallelepiped. Now, one note, even though the cross product has to be performed first, it actually doesn't matter in what order we write A, B, and C. You can write them in any order you want, as long as the cross product is performed first and the dot product is performed second. When you take the magnitude, you'll get the volume of the parallelepiped.